All right, welcome folks. This lesson is on one of the periodic trends, the atomic radius. Now, atomic radius, an atom doesn't really have a fixed radius. The electrons can be zipping around, and the only way to really find the atomic radius is by measuring the distance between the nuclei of two touching atoms, and then having it based on the equation just on the bottom here. So the radius is equal to distance divided by 2. So we're not going to get into that, just a kind of side note as to what atomic radius is. But let's look at the first trend. Let's look at the group trend. So going down a group. So remember that this is in group number 1, hydrogen, lithium, sodium, potassium, rubidium. Now what you can see here just right from the get-go is that as you move down this group here, you're seeing that the atomic radius, or as characterized by these spheres, is getting bigger and bigger and bigger. The question is, why? Well, remember that as you go down a group, what you're adding is you're adding electrons. You're increasing the number of electrons. And these electrons don't go into the same shell. The first 2 electrons go into that first energy level, and then when you add more electrons, it goes into that second energy level. So in that one, we can hold 8. Now, what if you had to add another couple of electrons? Well, you're going to have to increase the number of energy levels and start adding them onto that. So what you can see is that just by adding electrons, we're getting bigger and bigger and bigger. It's taking up more space. And as you know here, when we look at lithium that only has 3 electrons, and sodium that only has 11 electrons, okay, if it has more electrons, it's going to have to take up more space because it's going to have to occupy new and bigger energy levels. Not only that, but there's also an interesting thing happening with something called shielding. Now remember, that's from last lesson, shielding. As we add more electrons to these energy levels, for example, this one over here, it's now not as attracted as maybe these electrons are or this electron is to this positive nucleus. So what that means is that not only will it be farther out, but it also will have less attraction to this nucleus. If it has less attraction, that means that it's going to be held loose. Okay? If it's held loose, well, it can have a little bit more space to play. Okay? So not only does the atomic radius increase because you're adding electrons and adding energy levels, but at the same time you're also reducing the attraction between the positive nucleus and these outer electrons. If it's not being held so closely, these electrons have a little bit more freedom and a little bit more place to play, and so again, slightly, they're going to go up in radius. Now, what about the period trend? So going across a period. Now remember, across a period is always going from left to right, in terms of the left side of the periodic table to the right side of the periodic table. And as we can see at the bottom here, strangely, as we go from left to right, our atomic radius gets smaller. Now, why is this the case? Well, what you remember is that if you look across the periodic table in this period over here, we keep adding electrons. Okay, so let's say sodium, we're just going to draw the valence shell. The valence shell has only 1 electron. Magnesium, the valence shell, has 2 electrons. And this is all the same valence shell. Aluminum has 3 electrons. Silicon, 1, 2, 3, 4 electrons. So as you can see, what we're doing is that as we're going across this period, we're just adding electrons to the same energy level. Well, if there's more electrons, what should be happening? Well, because we're adding electrons to the same energy level, there's no increase in shielding because the inner electrons, the ones on the inside here, the 8 that are on here, the 8 in the energy level below them, that stays the same. So there's no effect of shielding. There's no change in the shielding effect. Okay? Again, the reason being is that shielding comes from these inner electrons. And all we're doing is adding electrons to the outer shell. We're not affecting how many inner electrons there are. And because we don't change how many inner electrons there are, the shielding effect does not change. So then what's the reason? Why is that as we go from left to right, the atomic radius is getting smaller? Well, as we go from left to right, what we are doing is that we are adding protons to the nucleus. Remember that all of these have a changed atomic number of 1. So here we have 11, here we have 12, here we have 13, etc., etc., etc. These also tell us how many protons we have. So we have 11 protons, 12 protons, 13 protons. So as we go from left to right, we're adding protons to the nucleus. Now, what does that do? Well, if we have more protons, we have a higher nuclear charge. We have a higher nuclear charge. So that means that this more positive nucleus creates a stronger force of attraction between itself and the electrons. And these pull the electrons closer in. So once again, as we add more and more protons, as we go from left to right, remember here we have 11 protons, 12 protons, 13 protons, 14, 15, the charge of the nucleus is getting more and more and more and more positive. And because it's becoming more and more and more and more positive, it's going to pull these electrons on the outer shell closer in. Remember, shielding stays the same. So that means that the effective nuclear charge that these outer electrons feel is going to be greater as we go on. Because the shielding stays the same, the only thing is that the inside positive item, the nucleus, is getting more and more and more positive. So it's going to pull these electrons in and have a smaller radius as we go to the right. So here's our general trend of atomic radius. Atomic radius, we can see that as we go to the left and as we go down, we see an increase in atomic radius. Remember that as we go down a group here, it's because we're adding more electrons and that those energy levels are increasing, which take up more space. As we go, and we'll just describe this way, as we go to the right, the increased nuclear charge is pulling the electrons closer as we move to the right. So as we move to the left, obviously the opposite is happening and the atomic radius is getting bigger. Now this is just a little table of values for it. What you can see is, again, remember that our general trend of atomic radius, so increasing atomic radius, is this way and down. So that means that items on the top right corner should technically be your smallest. Okay? And items on the bottom right corner will be your largest atomic radius. And if we look at the periodic table, we see that it's true. In the same period, hydrogen and helium has the smaller atomic radius. So it has the smallest atomic radius in the periodic table. And same thing here, when we look at the bottom left, cesium should have the largest atomic radius, and so it does. Okay, there's nothing else larger in the periodic table, at least in this view over here. Okay, so we see that, and it does fit our actual trend. Now, as you know, atoms gain and lose electrons to become to have a full outer shell or a full octet. Remember that metals generally tend to lose electrons and they become cations. Nonmetals tend to gain electrons, they become anions. So when a metal, for example, loses an electron to become a cation, remember cat paw, cats have paws, cat positive. Okay? Cations, they are generally smaller than their neutral atom form. So when we look at this, let's say, for example, we have sodium, okay, and it's in a gas state. It loses an electron and a plus gas plus one electron that it's lost. So in this case, sodium would be this one over here, and sodium plus would be this one over here. We're not talking about the actual values of their atomic radius. We're just simply talking about in general. Okay? So it's not exactly 180 and 100, but we're just looking at using this as an example. Now, why does this actually happen? Well, let's look at actually what's happening with the Bohr Rutherford diagram of sodium. So sodium has your positive nucleus in the center here. It has 2 electrons here and here. And then it has 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And then finally it has 1 valence electron at the end, on the 3rd shell. So what's happened is that it's actually lost this outer electron. If it's lost this outer electron, what does sodium look like now? So again, we have our positive nucleus here. Our first energy level has 2 electrons. And then our our second energy level has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Well, that other electron has been lost, so what we see is that there's no outer 3rd shell anymore. All we have is these 2 inner shells here. We have our first shell and we have our last shell. So what has happened is, let's look at the amount of shielding that has changed. Here, when we were focusing on this electron, it had to look through this first level and this second level to get to the attraction of the nucleus. Now, if we pick any of these electrons here, well, notice that we don't have a 3rd energy level anymore. So that means we have to focus on one of these electrons on the inside here. Any one of these only have to look through this first shell. This one had to look through 2 shells. This one over here only has to look through 1 shell. There's less shielding. There's less shielding for this one, and therefore these electrons are pulled in closer. Okay? Not only that, but now what we see is that in this case we had 11 protons and we had 11 electrons. Okay? In this case, we still have 11 protons. It's still sodium, but now we only have 10 electrons. In this case, the protons, outnumber the electrons. So there's more positive charge per electron. So not only is there less shielding, but there's more positive charge per electron, which means that the electrons are going to be brought in closer to the nucleus, and the atomic radius is going to decrease. The opposite is true for an anion. Anions are larger than their neutral atoms, so for the opposite reasons than a cation. As we add electrons, okay, the shielding doesn't really change that much because the inner electrons don't change. Okay? But what you're going to find is that the number of electrons outnumber the number of protons. So if we look at, for example, fluorine, okay, fluorine has 9 protons and 9 electrons in a neutral atom. When fluorine gains an electron to become fluoride, it still has 9 protons, but now it has 10 electrons. So what we can see is that there's less positive charge per electron. And because there's less positive charge, there's less attraction, so the electrons are not as tightly held by the nucleus, and they tend to move out a bit. Now, when atoms ionize, what we can see is a phenomenon called isoelectric, which means that they have very similar electronic configurations. So let's look at F, Ne, and Na when ionized. Now, first thing you should say, Ne is a noble gas; it doesn't ionize, and that is true. So let's look at fluorine and sodium, but we're going to draw a neon at the same time. So fluorine, okay, it has this 9 protons in the center. It has a first shell with 2 electrons. And then it has an outer shell of 1, 2, 3, 4, 5, 6, 7. So it only has to gain 1 electron. So let's let it gain that 1 electron. And it gains it from, for example, a metal. It's going to have an overall negative charge. Okay, so this is F minus. Ne, well, again, the nucleus will have 10 protons. In the first shell, it has 2 electrons, and in the outer shell, naturally, it has 8 electrons. So we're just going to fill that shell. There is no charge because it already has those electrons. And finally, let's look at sodium. Sodium has 11 protons in the center. First shell still has 2 electrons. And then we have our 8 electrons. And also know that sodium has that third outer shell with that last electron. But we're ionizing it. It's a metal. It's going to lose that outer electron. So what we can see is that we don't actually have that third shell anymore. It's lost that 1 electron. And this whole thing becomes positive. Here's your Na plus Ne. Now, what you notice about all of these three atoms or ions is that they all have 2 inner electrons, two inner electrons, and they also have 10 outer electrons. Fluorine gained 1 to get those, not 10 outer electrons, 8 outer electrons for a total of 10. They have 8 outer electrons, and fluorine gained that 1 electron to get that 8. Neon already had the 8, and sodium had to lose that 1 valence electron to get the 8 outer electrons. So what we say is that all these three species are isoelectric. Okay? They have the same electronic configuration. They have the same amount of electrons and the same amount of, or a similar configuration. They still are their own species, however. Fluorine is still fluorine because it has 9 protons. Neon is 10 protons, so it's still neon. And again, because this has 11 protons, it is still sodium. So they're still different elements, but they have similar electronic configurations. And again, so we call this isoelectric. And they're species or elements or ions that have the same number of electrons in a similar configuration. So here we have atomic radii of an isoelectric group of ions. These all have, again, they all have the same amount of electrons in the same configuration. They have 2 in the center, 8 in the outside. And what you can see is that their atomic radiuses change. Remember that if you become an anion, your atomic radius increases. As you become a cation, it decreases. So how do we know which radius is smaller? Is it the F minus, the Ne, the Na? They all have the same amount of electrons, but remember they do have a different amount of protons. So can we use that? Yes, we can. We can use Z effective. Remember that Z effective is equal to Z effective is equal to Z minus S. Z being the number of protons, S being the number of inner electrons. Okay, so let's calculate these for these 3 species. Fluorine has 9 protons, and it only has 2 inner electrons. Okay, it has the 8 in the outer shell, so we get 7. Neon has 10 protons, and again it only has 2, so here we have 8. And sodium has 11 protons, again it only has 2 inner electrons that are doing some shielding, and we have 9. The species with the largest Z effective has the smallest radius. Why? So try to come up with an answer, and we'll describe that in a second. So just go ahead, pause the video, write down an answer in pencil in your notebook, and then we'll come back and see if it's correct. Okay, so welcome back. What we're going to look at is why is sodium, the one with the largest Z effective, the smallest radius. Now in this case, when we look at fluorine, let's look at the ratio between positive and negative. Fluorine has 9 protons, and in this case, in this ion form, it has 10 electrons. Neon has 10 protons, 10 electrons, and sodium has 11 protons and 10 electrons. So right there you can see that these then when we look at neon, the protons and the electrons, they cancel each other out, and they'll have no charge. In fluoride, we have an overall charge of -1 because we have more electrons than we have protons. The opposite is true for sodium. Here we have +1 because we have more protons than we have electrons. And that is the key. That is the key. Because we have more protons than electrons, each of these electrons is going to be receiving more attraction. Okay? In all of these 3 species, the shielding is all the same. It's only 2 electrons on the inner energy levels. Okay, so the shielding is the same. So the difference in between these is how much attraction the nucleus is putting out. And because in sodium we have more protons, that means the nuclear charge is higher, and that means that the effective nuclear charge is also higher. The amount of feeling each electron gets from the nucleus is higher. Because there's more attraction, they're going to be pulled in closer, and that's going to reduce your atomic radius. So here's just a few charts that you have. You can see the comparison between the regular ion and the ion and the neutral atom. So for example, if we look at magnesium, we expect it to be smaller because it's a cation. It's going to pull the electrons in closer, and so it does. The same is true for anions. In case of oxygen, for example, you can see that as we add 2 electrons to get that full outer shell, it really increases in size. All right, guys, that's it for this lesson here. We'll see you in a bit for our next periodic trend. Bye.